All right, let's just jump right in. We're going to pull back the curtain on something that happens all day, every day, but feels kind of like magic. How your devices, your phone, your laptop, automatically get an IPv6 address and connect to the internet. We're going to break down the two key ways this happens, Slack and DHCP6. But seriously, have you ever stopped to think about that? You walk into a coffee shop, you connect to the Wi-Fi, and boom, it just works. How does your device know what its address is supposed to be? It's not random. It's actually this really cool automated dance that happens in seconds. And today, we're going to break down all the steps. And that right there is exactly why we need this automation. Can you imagine trying to type in one of those incredibly long, complicated IPv6 addresses by hand on every single device you own? It would be a total nightmare, full of typos, super time-consuming, just a mess. The thing is, IPv6 was built from the ground up, with the idea that devices should be able to figure this stuff out for themselves. So the whole process kicks off the very instant your device's network connection fires up. Before it can even think about talking to the wider internet, it makes this little address for itself called a link local address. This is basically the device's way of raising its hand on the local network and saying, "Hey, I'm here, I'm ready to talk." It's step one. Now, that link local address is great for chatting with other devices on your Wi-Fi, but to get a global address, one that can actually browse the web, the device needs some direction, and that's where the router comes in. You can think of the router as the conductor of the orchestra. It regularly sends out these special messages called router advertisements, or RAs, and they're packed with all the info a device needs to get configured. So how does the router give this guidance? Well, it's all cleverly encoded in 3 little flags inside that advertisement message. Think of them like little on-off switches. The A flag says, "Hey, you have permission to make up your own address." The O flag says, "You can make your own address, but you need to get other info, like DNS servers, from me." And the M flag says, "Stop. Don't do anything yourself. Get everything, your address, all of it, from a server." The combination of these flags sets the policy for the entire network. Okay, so let's follow that first path. Let's say the router turns on that A flag. That's the green light for something called Slack, which stands for Stateless Address Auto Configuration. This is what we call the do-it-yourself method. With Slack, the device pretty much handles everything. It listens for that router advertisement and grabs the first half of the address, the network part, right from the router. Then it gets creative and generates the second half of the address all by itself. And finally, before it starts using it, it does a quick little safety check to make sure no one else on the network came up with the same idea. So, how exactly does a device make up that unique second half? Well, there are 2 main ways. The old school method, called EUI64, actually used the device's physical MAC address to create it. It's clever, but it means your IPv6 address is forever tied to your specific hardware, which isn't great for privacy. That's why today, most modern operating systems just generate a random 64-bit number instead. It changes over time and is way better for keeping your device from being tracked online. Okay, but you might be thinking, what if 2 devices on my network randomly generate the exact same number? I mean, the chances are astronomical, like 1 in 18 quintillion, but IPv6 has a safety net anyway. It's called DAD, or Duplicate Address Detection. Before using the address, the device basically shouts out to the network, "Hey, is anyone using this address?" If it hears nothing back, it knows it's good to go. All right, so that's the DIY route. But what if the network administrator wants more control? What if they don't want devices making up their own addresses? Well, that brings us to our second path, DHCP-v6. This is the server-based method, and it's triggered by those O and M flags we saw earlier. This is the managed, top-down approach. When a device is told to use DHCP-v6, it starts a very quick 4-step conversation. First, the client solicits, basically asking, "Any servers out there?" A server then advertises its services. The client picks one and sends a specific request for info. And finally, the server sends a reply with all the goodies, the address, DNS info, the whole shebang. It's a simple, elegant negotiation. Now, DHCP-v6 actually comes in 2 main flavors. First, there's stateless. This is a hybrid approach. The device still creates its own address using Slack, but then it goes to the DHCP-v6 server only for the extra stuff, like DNS servers. Then you have stateful DHCP-v6. This is full-on control. The device gets absolutely everything from the server, its complete address, all the other settings, and in this model, the server keeps a detailed list, a state, of exactly which device has which address.
So we've got SLAAC for easy peasy automation and DHCPv6 for tight, centralized control. But how does this all look in the real world? And how do network administrators actually verify that everything is working the way it's supposed to?
One really important thing to remember is that routers in this whole system are incredibly flexible. A single router can actually wear a few different hats at once. It can be the DHCPv6 server for the devices on your network. At the same time, it can be a DHCPv6 client to get its own address from your internet service provider. Or it can act as a relay agent, just passing messages along between your devices and a big centralized DHCPv6 server somewhere else. So, for any network admins watching, how do you check on this? How do you see what's going on? If you're running a stateful DHCPv6 server, this command is going to be your new best friend. It literally shows you the server's database of bindings. It's the master list of which IPv6 addresses have been leased out to which specific devices. It's your single source of truth.
And if that first command shows you who has an address, this one shows you what's available. This command lets you check on your address pools. You can see how many addresses you have to give out and how many are currently in use. It's basically like checking the inventory in your warehouse. And that really brings us to the crucial points. The magic of your phone instantly getting online isn't magic at all. It's a very clear, very well-defined conversation between your device and the router. And it's all directed by those little flags we talked about. This elegant system is what allows modern networks to be so automated, so scalable, and so incredibly efficient. So that leaves us with a final, pretty big thought. As we start connecting billions, maybe even trillions, of new Internet of Things devices, from smart toasters to sensors, network admins are going to face this fundamental choice over and over. Do they lean into the pure, hands-off automation of SLAAC, which is easy and scales fast? Or do they opt for the centralized visibility and tight control of stateful DHCPv6, which is better for security and tracking? The answer to that question is really going to shape how the networks of tomorrow are managed, secured, and scaled. Definitely something to think about.